Welcome back to Physics with Miyoshi. I want to talk to you today about more kinematic stuff with constant acceleration. Today what I want to do is talk about these equations and how mathematically they come about and physically they come about. Especially these last two equations, they're more about mathematics than they are about physical, but I want to derive some of those and show you what they mean, like I said, both physically and mathematically. So, first of all, we want to figure out how we get that v is v0 plus at. Well, physically, if we know that we have a constant acceleration, we know that if I start out with an initial velocity, I can just add in that acceleration times my time to find what my final velocity will be. And we can see mathematically, if we just start with the equation, acceleration is delta v over delta t, then I can rearrange that guy to be the same as v final minus v0, or oftentimes they'll just get rid of the f for the v minus v0. And since we know that we can just set any initial time to time 0, oftentimes we'll have delta t, is t final minus t initial, or they'll just say delta t is t, which is what I'll follow that convention as well. So, if we rearrange this guy, multiply by t on both sides, then we end up with at is v minus v0. And then we can see all we have to do is rearrange this guy, add the v0 to each side, and we get v is v0 plus at. And I'll just swap that around. V is v0 plus a times t. Again, we can see that all I have to do is multiply if I have an initial velocity, multiply the time times the acceleration to add those together, and I'll get my final velocity. Okay? The second equation here, we need to know just a little bit, one more thing. When we have constant acceleration, if I have my v average, we can think about a v average just like we can with any average mathematically, and that is I take my two endpoints, if you will. I know it's going to be constant acceleration in there, so I can just take my final velocity, add that to my initial velocity, and divide that by 2. As long as it's constant acceleration, that will be true. So to get this guy here, all I need to do is rearrange this equation. So if I rearrange that equation and know this, I can say v is delta x. If I consider x to be like I did the other one, where my initial is 0, then I could just do x over t. Then if I rearrange that equation to find x, I know that x is v times t. And if I rearrange that guy, I can just do vf minus v over 2 times t, and that's this equation here. Again, if we could think about this physically, if I know that my acceleration is constant, my final and my initial velocity, I just add those two together, divide that by 2, and then I can know that my average velocity multiplied by my time is going to give me my final displacement. Okay? Alright. These last two are a little bit more mathematical and less physical. So, this equation, x is equal to 1, this is the equation here, x is v0t plus 1/2 at squared. That's the equation that I remember from way back when I was in high school. I could quote that off over and over again. So I can get this guy from these two equations here. The one I just showed you now, x is 1/2 v0 plus v times t. And this other one here that I just showed you, v is v0 plus at. So what I'm going to do is I'm just take this v here and I'm going to substitute that guy in there mathematically. So I end up having x is 1/2 v0 plus v0 plus at times t, which is just substituting this guy here for the v, and then I get 1/2. Well, v0 plus v0 is 2v0 plus at times t. And then I'll just distribute the 1/2 through here, and that gives me 1/2 times 2 is 1, so that's v0. 1/2 times at is 1/2 at, so I'll just do that. 1/2 at, and then I distribute the t through there, and we get v0 times t plus 1/2 a t times t is t squared, and there I get that one as well. So we have that equation there. X is v0 times t plus 1/2 at squared. So if you know the acceleration and you know the time and you know the initial velocity, we can find our distance. All right, the last one I want to derive for you is this guy here. I personally rarely will use that equation because I can use these two guys, and the other three, I'll use these three over this one almost all the time. I'll just combine a couple of things. But let's show how we get that. So if I start out with this, x is 1/2 v0 plus v times t, and that remembering that the acceleration is my change in velocity over change in time, I can now rearrange this guy. Let's go. That is, acceleration is my v final minus v0 over t. And again, most people will just get rid of the vf and just call that v. If I look at this guy here, I can now rearrange that to solve for t, and then I just get t is v minus v0 divided by a. Now if I substitute this guy in for t up there, so if I substitute that guy in, oopsie, this guy here, in there, then I have x is 1/2 v0 plus v times this guy right here, which is v minus v0 over a. Okay, I'll bring the a out of here, so I get 1 over 2a. And then this, if you recognize this, we'll just rearrange it to v plus v0, v minus v0. Hopefully you recognize that as a difference of squares, so we can just do 1 over 2a is v squared minus v0 squared. And then I can rearrange that finally to be v squared minus v0 squared is 2ax. Multiply the 2a to both sides. 2ax, and then we get that final equation. Rearrange it, and we get v squared is v0 squared plus 2ax. Again, this equation here, because I can use these equations to get there, I will personally never or rarely use this guy, but if I'm in a hurry and I know the 3 of the 4 of those values, I'll use this too. So, again, this is just more the derivations of why these two come about and how these physically come about, as well as the mathematical derivations. But I want to explain a little bit more about the kinematics of constant acceleration and how to use, or how these equations make sense both mathematically and physically. So, tune back in again for more Physics with Miyoshi. Next time we'll talk about more kinematics.